Good afternoon, computer scientists, and welcome to our 10th GCSE Livestream. Woo!
Hi, everyone. Wow, I cannot believe we're 10 sessions old.
You don't look a day over 8 sessions, Laura.
Thanks, Pete. What's been your favourite session so far? I've got to say your visit to a reservoir for variables and constants has got to be up there. Let us know in the chat below what your favourite session has been.
Well, I think my favourite session so far is Di's last session on linear search. And I'm not just saying that because she's back with us today.
Very smooth, Pete. Yes, we are very excited to have Di back with us today for the second of our sessions on standard searching algorithms. If you weren't able to join us for our last session, you'll find it in our live stream gallery.
And today we will be looking at binary search. So let's bring Di into the stream to tell us more.
Hi.
Welcome back.
Hey Laura, hey Pete, lovely to be here again.
So Di, you'll be taking us through binary search today?
Yeah, that's right. This is the second of our standard searching algorithms. So it builds on last time's live stream, but hopefully you can follow it even if you didn't see that.
Sounds fantastic. And remember, everyone, if you have any questions for Di as she's presenting, you can send them in the chat or, of course, by using the question form below.
So, Di, if you're ready, you can take it away.
Great, thank you. Okay, so we're going to look again at searching. And the reason we concentrate on searching is because it's one of the most common procedures, one of the most common problems that you'll face in computer science. Computer systems collect masses and masses of data, and we need to be able to search that data to find the information that we want from it. So, for example, you might love online shopping, and you might regularly go onto sites and search for things that you want to buy, maybe a new pair of trainers or a computer science textbook. You've probably got music playlists or film playlists on video streaming sites, and you want to look for a particular film or something to play to keep you relaxed while you're doing your computer science homework. So in all of these instances, you will use a searching algorithm to find the information you need. And last time, if you joined the previous live stream, we looked at the task of finding an item in an unordered list. And we looked at the example of my bookcase, which is stored in completely random order, so no particular order at all. And we learned that the only safe way to search that was to start right at the beginning and to look at each book in turn until we found the one that we were looking for. And that algorithm was called a linear search, like a straight line, working our way through from one to another. So today we're going to look at how this will change when we look at an ordered list. So when we talk about an ordered list, we're talking about the items in a list being in a particular order. And that could be alphabetical order, like you can see the little excerpt from a recipe book on the slide, or there might be a numerical order. They could be from high to low or low to high, but they are ordered in some way. So the example you can see on the slide is from a recipe book. This index has got well over 1,000 different entries. And when I'm thinking about something to cook, then I'm going to look in the book to see if I can find a recipe for whatever I have in mind. So I've opened the book in the middle, and we can see that it's found some recipes with mangoes in them. But what I really, really want to cook is some chocolate brownies. So maybe I could ask one of my co-presenters, Pete, if you open the book and you saw this page on mangoes, where would you go next to try and find a recipe for chocolate brownies?
So because I know that C is before M in the alphabet, I'd go before, so I'd go earlier in the book.
Perfect. And really important now, Pete never has to look at that second half of the book. Okay, he knows that he's going to find chocolate brownies somewhere in that first half. And this is the principle that we're going to use when we develop the binary search. Okay, so let's have a look at the method then. So we're going to start then by looking right in the middle of the list. And with a binary search, we always start in the middle. So we'll open the recipe book, have a look at the very middle entry, and we'll compare it to the one I'm looking for. So let's say mangoes was in the middle. I want chocolate brownies, and therefore I'm going to discard the whole of the upper part of the book, and I can now focus my search on the first half of the index. And at this point, I'll just repeat the process. So I'll look at the central item of all of the ones I've got left, the first half of the book. And again, I'll do that check, a chocolate brown is before the one I'm looking for, is it after? And again, I can discard half of the list. And I'm going to keep repeating this process. I'm going to keep checking and discarding half until I find the one that I'm looking for. And this approach to solving a problem is sometimes called a divide and conquer approach. So what we're doing is we're dividing the problem. We're making it smaller and smaller until we can solve the problem. Because at the end, I have one item left. It's either the one I want, and if it isn't, then the thing I'm looking for, that elusive chocolate brownie recipe, is not in the list. So let's just recap on the purpose of the algorithm. So the purpose is to find something in a list of items. If the item is found, the algorithm is going to return the position of the item in the list. So you may recall that if we look at a list or array of items, every slot is given an index. The slots start from 0. And in this example, we've got indexes 0 to 8. If we find the item in the list, it's going to return the index position where we found the item. And if the item is not found, the algorithm is going to return -1. And it does that because -1 is what we call a rogue value. It's not a possible index. So we know that if the algorithm returns -1, that the item wasn't in the list. And let me just repeat, because this is really important, you can only use a binary search on an ordered list. And hopefully this will become apparent why as we progress through the algorithm. Okay, so I'm just going to make sure that my co-presenters are paying attention and not too busy celebrating the 10th episode. So let me just ask Laura. Laura, remind me where we are going to start searching.
Oh, I'm glad I'm switched on, Di. I think we start in the middle position.
Perfect. Okay, so we've got a little reminder there. I think that's Laura there picking out an item from the middle of the list. Thanks, Laura. That was great. Okay, so searching starts in the middle of the list, and we refer to the middle of the list as the midpoint. Okay, so this is a term I'm going to use during the explanation. And the other really important terms that we need to follow are the first and the last positions of the list. So at the start, at the outset, the first position, the index of the first position is 0. And the last position, the index of the last position is 8. And we're going to calculate the midpoint. And we're going to do that by adding together first and last. 0 plus 8 is 8. And we're going to divide it by 2 to get the midpoint, which is 4. And then we're going to look at the value at the midpoint, which is 12. You can see that's highlighted with the green rounded square. And we're going to compare that to the value that we're looking for, which is 16. So 12 is less than the value we're looking for. So we know now that the value that we're looking for, 16, must be in the upper part of the list, if it is in the list indeed. So at this point, we can discard the lower part of the list, and we can discard everything right from the beginning up to and including the midpoint, because we've checked the midpoint. We know that's not it. So now if it exists, it must be in the upper half of the list. So you can see there, we've just grayed that out. So you can see now a big portion of the list now can be discarded. And now we have a smaller list. So we have a new problem, a much smaller problem, which is finding the item in this smaller list. So we're going to adjust the pointers. We don't have to adjust the last pointer because the last position is the same, but we do need to adjust the first pointer. And what we're going to do is add 1 to the midpoint. So the midpoint was 4, we add 1, the first item is 5. And as I said, the last pointer remains the same. And our list is now everything from slot 5 to slot 8 of the list that we've got. And we calculate a new midpoint. So again, we add first and last. So we add 5 and 8, we get 13, and we divide it by 2. And now we're going to encounter a little problem because it wants us to examine slot 6.5, but clearly there is no slot 6.5. So we have to either round that result up or down. So we can either look in 6 or 7. It doesn't actually matter for the algorithm so long as we're consistent. But you will find if you examine the standard algorithm that it uses floor division, which you may have come across. So there are 3 division operators that we can use in our programs. There's normal division, there's floor division, which just gives us the integer part of an answer. So if I divide 13 by 2 and I get 6.5, it just discards the half and I get 6 as a result. And the other type of division is modulo division, which isn't relevant to this particular algorithm, but something you might like to look at later. So 13 div 2, that's the floor division, gives us 6. So we're now going to set the midpoint to 6. So we've got first as 5, last as 8, and our midpoint as 6, slightly off center. And we examine the value at the midpoint, which is 23. Remember, we're looking for 16. So this is more than the value we're looking for. So what we can do now is we can discard the upper half of this smaller list, what remains of the original list. And remember, we can also discard the midpoint. So we're now going to discard everything from 6 to 8. Now, clearly, you can see there is only one item left. But remember, your algorithm is following a set of instructions over and over again. So actually, we need to continue running the algorithm. So what we're going to do is we're going to update the last pointer. This time, we're going to update the last pointer because we've discarded the upper part of the list. And we set the last pointer to midpoint -1. Okay, if you remember, last time we sent first to midpoint +1. This time, we're taking last. So setting last to midpoint -1. And the first pointer remains the same because I haven't changed that part of the list. And we calculate the midpoint. So 5 and 5 is 10. We're consistently going to use div now, floor division. So 10 div 2 is 5. And interestingly, we now have midpoint first and last, all pointing to the same part of the list. And this will always happen on the very last comparison if we get that far. And we're going to look at that item and see if it's the one we're looking for. And lo and behold, it is. So we have completed our search and the algorithm will return the value 5, which is the index position where we found the item. Okay, so let's talk our way through the method. So let's have a quick look at the efficiency of this algorithm. So we were looking for the value 16. Pete, how many slots of the array did we inspect?
There I am.
Yeah. So how many slots did I look at? Because obviously I talked quite a lot. There were quite a few slides, but how many slots did I actually examine?
Sure, it was a good job I was paying attention, then, wasn't it, Di? So you inspected 3.
Absolutely spot on. So you definitely were paying attention. So we can see here on this slide, we first of all went in at the first midpoint, which was 4. We looked at that one. It wasn't the one we were looking for. We then looked at the next, that was 23. It wasn't what we were looking for. And then we calculated a final midpoint, which was at 5. And that was the item that we were looking for. So we made 3 comparisons. Okay, so having made sure that Pete was paying attention, I just want to make sure again that Laura is paying attention. So Laura, if you remember last time we did a linear search, which was completely different. If we carried out a linear search of this same list, how many comparisons would we have done?
So you're checking I was paying attention last week as well, you see. With a linear search, we would have to look at each item in turn. So you would have to have looked in 6 positions to find the value of 16.
Perfect. Can you tell me which positions we would have looked in?
Because our indexing starts at 0, we'd start at 0, then we'd look at 1, and then 2, 3, 4, and then 5, and find the value of 16.
Perfect. Okay, so we can see now that even with a very small array of numbers, that the binary search was actually more efficient. So with the binary search, we made 3 comparisons. And with a linear search, we made 6 comparisons. And when we're comparing searching algorithms, this is what we call the fundamental operation. It's the amount of times that we have to compare something in the list until we either find what we're looking for, or we can categorically determine that the item is not in the list. That's just a little recap of the positions for the linear search. Okay, so just a little reminder then of how efficient this binary search is and how we can calculate the number of comparisons that we need to make. So every time we make a comparison with binary search, we can say that the slot we're looking at either contains the item we're looking for or it doesn't. If it doesn't, we halve the list. And then we keep moving on, we keep comparing and halving, and eventually, unless we find it earlier in the process, we only have one item left. In which case, as we said before, this is either the item we're looking for, or we can be totally certain that the item isn't on the list. So the answer to how many comparisons can be determined by answering the question, how many times can we halve the size of the list until we have just one item left? So let's look at a bit of maths, because we always like a bit of maths. So first of all, let's look at the case where there are 10 items in the list, slightly bigger list than the one I used, in fact. And let's just do that maths. So 10 div 2 is 5. That's the first halving. 5 div 2 is 2. Next one, 2 div 2 is 1. That's the third halving. And we obviously have to do the final comparison, which is to look at that one left over. So if we have 10 items on the list, we do 4 comparisons. Now, interestingly, you'll see the maths is, it is quite fascinating, because if we have 100 items in the list, we actually only need 7 comparisons. And if we have 1 million items in the list, we only need 20 comparisons. And I calculated how many comparisons I needed for my cookery recipe index. And it's, as I said, it had just over 1,200. And I would only need 11 comparisons to definitively find that recipe for chocolate brownies. So binary search is very efficient indeed, and particularly with really large lists. And another way of looking at this is to see that performance on a graph. So the blue line is a linear search. As you expect, like it sounds, it goes up in a straight line. The number of comparisons is always equal to the number of items on the list. Whereas a binary search gives us a much flatter line, that even when we get really big figures, we don't actually have to do that many comparisons. It's a really efficient searching algorithm. Okay, now in an exam, you may get asked about the pseudocode for a binary search. And on the Isaac Computer Science platform, you can see this algorithm and, with some comments and explanations around it. I'm just going to pull out the sort of key points, really. So the main thing is that we have a while loop, and we keep on searching. The first part of the search criteria is while first is less than or equal to last. So basically this means while there are still items to search. And remember, we carried on searching even when first and last were equal to each other. And that's really important to make sure that we always examine the last slot. And obviously, we can also stop searching when we found the item. So once we found it, we don't need to carry on searching the rest of the list. So this is the criteria that control the loop. So while we still have items to search and while we haven't found it. And then inside that loop, I've got this on 2 slides because quite a lot of code here, although there's a fair lot of comments to help you understand the code. So what you can see here is inside the code, you can see the calculation of the midpoint, first plus last div 2, as I explained previously. We then check the item at the midpoint. If it's the one we're looking for, we set the found index to the midpoint value and a little flag to be true. That's going to stop the looping. And otherwise, we're going to adjust either the first or last pointer. So you can see here that if the item that the item at the midpoint is less than the search item, then we adjust first, and otherwise we adjust last. So actually the code there is not really, it's quite a bit of it, but it's not really that complex. And hopefully, so long as you have a mental model of the procedure, you will be able to make sensible suggestions around any questions you're asked about the pseudocode. But as I said, I really would encourage you to study it on the platform and to take your time to go through it slowly and to answer the questions that we have on the platform as well. And also on the platform, you can find real code examples. So hopefully you've seen already, we've got examples in both Python and C#. And under each code example, there's a link to GitHub. You can download the code and then you can run it yourself and you can tweak it. There's some test data in there that you can use to make sure that it works.
Well, thanks very much, Di. That was absolutely awesome. We have had some questions in from the audience, I think. Now let's have a look at this one. Are there any occurrences when we would choose to perform a linear search instead of a binary search?
Yes. Well, there's a really short answer to that one, which is that if you don't have an ordered list. So remember, this will only work if you can be confident that we can discard half the list. So if the items are all over the place in any kind of order, just because it isn't at the midpoint, we don't know whether it's earlier in the list or later in the list. So we wouldn't know which half to discard. So if your items are not in order, then you can't use a binary search. You would be using a linear search instead.
Brilliant. Some great questions there, everyone. And thank you for joining us, Diane. We have covered some really important topics in these sessions.
Oh, sorry, I just realised I should probably say thank you for having me. It has been a real pleasure to, it's always fun to talk about algorithms. You know, computer scientists love nerding out about that. So thank you very much for giving me the opportunity.
Absolutely. And also your explanation of how linear search compared to binary search was really interesting in terms of efficiency. Only a maximum of 20 comparisons for 1 million items. Wow. It was also fantastic to see a real life use for integer division as well. I've often been asked why GCSE students need to learn about integer division, and you've really clearly given us one use for it right there. If you're interested in finding out more about integer division and other arithmetic operators, head to isaaccomputerscience.org and search for operators. So thanks very much for joining us again, Di. That's been amazing. Thank you. Thanks, Di. Okay, as always, we've put together some questions for you to test yourself on everything you've learned today. You'll find them in the chat, and of course, they are linked below. Please do let us know how you found today's session by filling out our feedback form below. And as always, let us know if you have any suggestions or topics that you would like us to cover in future sessions. In our next session, we are going to be joined by GCSE Livestream veteran Matt Bowley for the first 2 sessions of sorting algorithms. So if you haven't done so already, you can book your place on our events page, and it is either below and also in our chat too. Okay, well, we look forward to seeing you then. Thanks very much. Bye, everyone.